Hello everyone, welcome to the 19th video of our lecture series. So in our last 2, 3 or more videos, we have talked about time independent non-degenerate perturbation theory and degenerate. So basically we have talked about time independent perturbation theory. So now in this video and upcoming videos, I will be talking about time dependent perturbation theory. So basically up to now, what in time independent theory, what we have done, we have assumed that the potential energy is independent of time. So that means if we have the potential energy, so that we have assumed to be only a function of position. So it is not a function of time. So potential energy is independent of time, and in that case our Schrödinger equation So what is our Schrödinger equation? Schrödinger equation is H psi. It will give us I H cut del psi del T. So this can be solved by the separation of variable. So psi we can write as psi r e to the power minus I E T by H cut. So this we can write for potential which is independent of time. So here this psi r is so for if we can write our wave function in this form, then our psi r will satisfy the time independent Schrödinger equation. So psi r and what is our time independent Schrödinger equation? It is H psi E psi. So where E is what? E is the energy eigenvalue of our corresponding Hamiltonian. Now, because the time dependence of separable solution is carried out by the exponential factor, so time dependence is absorbed in this exponential factor. So whenever we are going to construct any quantity which is physically relevant, like probability or expectation value. So these are our quantity of physical interest. So psi has no physical relevance. So if we want to calculate probability, then what we will do? We will calculate psi RT squared. So in that case, in this quantity, we can see that the exponential factor, which it will be cancelled out, because this we can write as psi star r e to the power I E T by H cut, and we have e to the power minus I E T by H cut and psi r. So it will be just psi r squared. So for our quantity of physical interest, here we have no time dependence, since even there is a time dependence in psi RT, but that only contribute to the phase part. So our physical quantity of physical relevance, they doesn't contain any time information. So you can say we can form any complicated linear combination of the stationary states, and we can obtain some wave function which has some interesting time dependence. But even even then the possible values of the energy and like this probabilities, these will all be constant. So if we really want to allow transitions, like we can say quantum jumps as they sometimes called. So if you want to allow some transition between one energy level and another, so suppose we have an energy level here and we have another energy level here. So suppose this is psi A, psi B, denoted by psi B, and it has energy value E A, E B, and we want our particle or whatever the system it is, we want to transfer it or allow its transition from one state to another, then we must introduce a time dependent potential. So, like in case of time dependent potential, there are like very few problems which are exactly solvable in quantum dynamics. But however, if our time dependent portion of the Hamiltonian is small compared to the time independent part, so like in non-degenerate case, like in time independent case, we assume our Hamiltonian to be H0 and HP. And we also consider that this is small compared to H0, and after that we apply our series analysis, and in that way we find out part of energy levels and energy values. So in the similar fashion, here we are also assuming. So now what we are doing, we are assuming this to be time dependent, and this is time independent. So what we are telling, we have our Hamiltonian, which is a function of time. So it consists of two parts. One is time independent. This doesn't depend on time. And we have another term which is time dependent, and also this is small compared to H0. So HPT at any time is small. So you can write like this way. So in that case, so if it is the case, then we can treat this HP as perturbation. So now we have to solve our problem for a perturbative Hamiltonian, which is a function of time. So let us proceed. So before proceeding with perturbative treatment, let us first understand two-level system. So this two-level system is like the simplest and very important topic in this time-dependent theory. So basically, it allows us to understand how this energy level, how atomic system or anything make transition from one to another. So before it is always handy to before further proceeding, let us brush up or learn how this two-level system works. So basically, so to begin with, suppose that we have two states of the system. So we have an unperturbed system, and in the system there are only two states. So they are psi A and psi B. So these are states of a system which is unperturbed. So now, if our unperturbed Hamiltonian is H0, then H0 psi A it will give us an energy value corresponding to the state psi A, and H0 psi B, it will give us energy value corresponding to the state psi B. And also these states, they are orthonormal. That means psi A, psi B in general we can write it as delta AB. Now since these two states, the system only consists of two states and they are orthonormal, so basically they forms the basis, and any arbitrary state we can express them as a linear combination of psi A and psi B. So that means this is an arbitrary state psi. So let us say psi 0. So this is our arbitrary state, and which is a linear combination. So suppose we have CA coefficient psi A and CB psi B. So here this wave function can be anything, like it can be in position basis, like position space wave function, or it can represent spin of the electron, or anything, or any more exotic, like suppose it can also represent the up spin, down spin, and any other thing. Basically it doesn't matter. So basically all we are concerned is about the time dependence of the system. So when I will write psi t, I will simply mean that the state of the system at time t. So if we don't have any perturbation, then each component evolves with its characteristic exponential factor. So that means for unperturbed system, we have our psi t to be Ca psi A, and how it will evolve? It will evolve with e to the power minus I EAT by h cut, and this term we will have CB psi B e to the power minus I EBT by h cut. So here and this Ca squared, this is the probability that the particle or the system is in state psi A. So this is so that means whenever we we measure the value of energy, so we will get energy value EA with probability Ca squared, and CB square also represents the same, like like whenever we will measure energy, the probability of finding the energy to be EB is CB square. And also from orthonormality condition, from normalization, we can ensure that Ca square and CB square that will surely be 1, because these two state forms the system. So whenever we measure energy, we will either find it to be EA or EB. So that means the probability of Ca square and the summation of Ca square and CB square, this should be 1. Now suppose that we turn on a time dependent perturbation. So suppose HT, we turned it on. Now this, since psi A and psi B, they constitute a complete set, so the wave function psi t, we can still express this as a linear combination of them. So like so we can write still psi t, even with this perturbation, we can write it as Ca psi A e to the power minus EAT by h cut plus CB psi B e to the power minus IEBT by h cut. So like you can ask what is the difference between these two. So the only difference is that when we have don't explicit time dependence in our Hamiltonian, these coefficients are constant in time. But now whenever we are turning on this time dependent perturbation, these coefficients now they will depend on time. So this is the key difference between between our Hamiltonian, which has time dependence and time independence. So now the our whole problem is to determine the CA and CB as a function of time. So we so what our main problem is, we want to know how this CA and CB they evolve with time. So for example, suppose that at time t equal to 0, we have our system to be in state psi a. So that means our CA at time t equal to 0, this is 1, and we have our CB at t equal to 0 to be 0. So that means initially the system is in state psi a. And now suppose at some later time, so suppose at t equal to t1, we do the measurement and we find that CA at time t equal to t1 is 0 and CB at time t equal to t1 is 1. So that means what are happening in the system? System underwent a transition from where? From psi A to psi B. So in considering this scenario, we can report that the system undergoes a transition from psi A to psi B. So now how we can find the time, this factor CA and CB, and how we can know how we can know how they are evolving in time. So basically we have to just plug this in our Schrodinger equation. So we have our original Schrodinger equation to be H psi I H cut del psi del t. Now we have our H to be H0. So this is time independent and time dependent part of the Hamiltonian. So if we plug this and our psi this in our Schrodinger equation, what we will get? We will get the following equation. So CA H0 acting on psi A e to the power minus IEAT by H cut plus CB H0 acting on psi B e to the power minus IEBT by H cut plus CA H prime psi A e to the power minus IEAT by H cut plus CB H prime psi B e to the power minus IEBT by H cut, and in the right hand side we will have this time dependence of this derivative of psi. So we have to just take derivative of this, and here what are the time dependent part? This is time dependent, this is time dependent, and these two. So psi A and psi B, they are not time dependent. So we will get in the right hand side I H cut, we can take this common, and we have CA dot psi A e to the power minus IEAT by H cut plus CB dot psi B to the power minus IEBT by H cut plus we have derivative of these terms. So we will get CA psi A, derivative of this will give minus IEA by H cut, and we have our e to the power minus IAT by H cut, and the last term will be CB psi B minus IEB by h cut, and we have here e to the power minus IEB t by h cut. Yeah. So this is our this is we are getting from our Schrödinger equation. So if we look carefully this term, now we know this H0 psi a, what will give? It will give us EA psi a. Similarly, H0 psi b will give us EB psi b. So this term and this term, so if we multiply I squared with this, and so then this term will be boils down to this. Similarly, this term will boil down to this. So these two terms in the left hand side and these two terms in the right hand side, they will cancel out. And if they cancel out, then from this equation we are getting CA H prime psi a e to the power minus IEAT by h cut plus CB h cut psi b e to the power minus IEB t by h cut, and then in the right hand side we have I h cut CA psi a e to the power minus IEAT by h cut and CB psi b e to the minus IEBT by h cut. So now we want to what our goal? Our goal is to know the time dependence of this. So for that, what we can do, if we look carefully, so this will give us how the CA will evolve with time. So from this we want to know information about CA prime. So what we can do? So here we can see that we have our psi b. So if we multiply both sides, like taking inner product with psi a, so if we do this, then this term will give us 0 because this is 0. So by taking, so basically this is standard trick. So by taking the inner product with psi a, so by taking this and using this orthogonality, so what we are getting, we will get CA psi a h prime psi a e to the power minus IEAT by h cut plus CB psi a h prime psi b e to the power minus IEBT by h cut, and here we have I h cut CA prime. So psi a will give us 1, and we will have e to the power minus EAT by h cut, and next term psi a psi will be, so that will give us 0. So now for our convenience we will define like Hij. So Hij prime is nothing but the matrix elements of this operator for our state psi i's. So it will basically be psi I h prime psi j. Now we also know that our Hamiltonian is Hermitian. So hermiticity of this h prime, it ensures that Hji prime, so what it will be? It will be psi j psi I. So it is basically psi ij star. So now if we multiply this by, so multiply, so here we want to have only CA dash. So what? With what we have to multiply? We have to multiply with minus I by h cut e to the power IEAT by h cut. So if we do that, we will get CA derivative, that means time evolution of Ca, it will be minus I by H cut and here we will have like Cb H. So this is Ca. So Ca H A prime plus Cb H AB prime e to the power minus I Ea minus, so it will be Eb minus Ea T by H cut. And in the similar manner, if instead of psi A, now if we take inner product with psi B, and then we multiply again by minus I by H cut e to the power I EBT by H cut. So if we do that, then we will end up with Cb derivative, that means time evolution of Cb. So it will be minus I by H cut Cb H BB prime plus Ca H BA prime e to the power minus I Ea minus so what it will be, we have this and we are taking inner product with IEB, so it will give us, yeah, so minus Ea minus Eb T by H cut. So this equation and this equation, so from this we can determine CAT and CBT provided we know our initial condition. That means we know our Ca at time t equal to 0. It can be 0 or it can be anything. So this is known, and also Cb at time t equal to 0 known. So it doesn't necessarily to be at 0. It can be at any time value. That means since this is first order equation, we have to know our two initial condition. So if we know our two conditions, then from that we can solve this and we can determine how this Ca and Cb they evolve with time. So so basically like for any general case, basically the diagonal matrix elements of H prime vanish. So HAA prime, HBB prime, this vanishes. This is a typical result. So if that is the case, then we can simplify Ca and Ca prime to be. So Ca prime in that case will be I by H cut HAB prime e to the power minus I omega 0. So I am writing what is omega 0. I will write down later. Cb, and we have our Cb prime to be minus I by H cut H BA prime e to the power I omega 0 T, and we have our Cb. So what will be H omega 0? Omega 0 will be EB minus Ea by H cut. Yeah, EB minus Ea by H cut. So from these two equation we can find how Ca and Cb evolve. So like so far we haven't made any assumption about the size of the perturbation. So till now what we have done is everything is exact. So now if H prime is small, then we can solve this equation by some successive approximation. So suppose that the particle starts out in the lower state. So that means Ca at initial time is 1 and Cb at initial time is 0. So if there is no perturbation, then the system would stay this way forever. So now we will solve this equation by a process of successive approximation. So now let us solve our zeroth order approximation. So zeroth order. So CA at zeroth order at time t is 1 and CB in zeroth order time t is 0. That means zeroth order means we don't have perturbation, and since we don't have perturbation, as CA initially 1, it will remain 1, and CB initially 0, so it will remain 0, because without any time dependence of our Hamiltonian, we don't have any transition. Now we will calculate the first order. So what we will do, to calculate the first order, we will insert these zeroth order values into our right hand side of our this equation. So first order to calculate, we will insert so if we denote this by 1 and by 2, so we will insert zeroth order values in 1 and 2. So what is CA derivative? CA derivative is minus I by h cut h a b prime, and here we have e to the power minus I omega 0 t CB. So first order, in first order what we will have? We will have I by h cut h a b prime e to the power minus I omega 0 t CB zeroth order. But this CB zeroth order at any time, so this is basically a function of time, this is 0. So we will have our first order derivative to be 0. So dCA of first order time derivative 0. That means CA1 at any time, this will be 1. And from 2 we will get CB prime at first order to be minus I by h cut h b a prime e to the power I omega 0 t, and we have here CA0t, and CA0t is 1, so it will be multiplied with 1. That means we will have our CB first order correction to be minus I by h cut from 0 to t h b a prime t prime e to the power I omega 0 t prime dt prime. So now in this manner we can calculate the second order, third order, and so on. So we will calculate the second order. So second order. So for second order we can write dCA2 dt, this to be minus I by h cut h a b prime e to the power minus I omega 0 t, and here we have CB1. So we have to insert this term here. So we will get again we have minus I by h cut from 0 to t h b a prime t prime to the power I omega 0 t prime, and it will be dt prime. So from that we will get our CA2 second order term to be, so if we do this integral, we will get 1, because our CA1 is 1, so we will get 1 minus 1 by h cut square integration from 0 to t, and we have here h a b prime t prime e to the power minus I omega 0 t prime and another integral. So we will represent this by 0 to t prime, and here we have h b a prime. So we are denoting this by double prime, and we have here I omega 0 t double prime dt prime, and here we have dt prime. So this is how CA2 evolve with time, while CB2 is unchanged, because so you can easily see that CB2 at t is CB1 t. Now if we notice that this CA2t, it includes the zeroth order term, and like what is this? This is basically the zeroth order term, and the second order correction would be the integral part alone. So this is our second order correction if we notice carefully. So in principle we can go this way, and we by this like we can always insert our nth order approximation into the right hand side of our equation 1 and 2, and by inserting nth order approximation, we can solve for n plus 1th order. So by inserting nth order approximation into 1 and 2, we can solve for n plus 1th order. So we saw that the zeroth order, it doesn't contain any factors of h prime. The first order contains one factor of h prime, and the second order correction has two factor of h prime, and so on. So and the error in the first order approximation is evident in the fact that CA1t, if we notice carefully, that CA1t and CB1t squared, this is not 1. This should be 1 because the probability summation should be 1. So in the first order approximation there is some error. However, this CA1t square and C1B1t square, this is 1 to first order in h prime, so which is all we can expect from a first order approximation, and the same goes on for the higher order. So this is it for today's video. So in the next video we will calculate, or we will consider a special case, sinusoidal perturbation. So our perturbation will be in the form of a sine function. It can be sine or cosine. So basically we have sinusoidal perturbation, and we will see for that case how our this coefficient of both the states evolve with time, and we will calculate the corresponding transition probabilities and so on. So we will meet on our next lecture video.